back again. This is going to be part number 4 and episode number 23. Again, this is about basically groups, context, communicators, and caching in MPI, chapter 7. So we're going to continue from where we left off. So we're talking about the inter-communicator scenario within this sort of operation, which was called as MPI create. It basically takes a pre-existing communicator and tries to generate a substantive group of those processes and put it into a new communicator. And we said that this communicator can be an intra-communicator and it can be also an inter-communicator. In this case, we said that we are basically mimicking the style of this example, which is visualized in MPI standard. So let's take a look at our example. It was called as what? MPI create inter. So you see that we have 6 processes on the left, 5 processes on the right. 6 plus 5 is going to be 11. So that is why we have the only valid value for the number of processes is 11, because we want to mimic this. And then we do the splitting, and you already know that what this part means. This is super, super important. You have seen it like in billions of those examples. So we need to have an original sort of intercommunicator. And that is why we use basically this thing, so that processes 0 through 5 are going to be a part of group A, and processes the next 5 processes, so the first 6 processes are going to be in group A, and the next 5 processes are going to be in group B. So that is why I put here an equal sign when we are doing the board size divided by 2. So 11 divided by 2 is going to be 5 something, but it's an integer division, so it's going to be 5. So we are including that 5 as well. So that means processes 0, including process 5, are going to be in group A. They're going to have this color of 0. That's group A. And the rest of those processes, which is process 6, 7, and all the way to 11, all the way to 10, because we start from process 0, are going to be in group B. So that is what we do with this coloring stuff. And also what changed here is that here we also put a +1 here as the remote leader, because group A needs to pass what's going to be the group leader of group B. It's going to be process so 0 through 5 are going to be in group A. Process number 6 is going to be in group B. So that is 11 divided by 2, 5 something. That something is going to get dropped because it's an integer division. So 5 plus 1 is going to be 6. So everybody needs to put this remote leader as process 6 in group A. Everybody in group A needs to put this process 6 as the remote leader. And that ranking is the ranking that they have in the peer communicator, which is this MPI world. And all the other processes in group B, they're going to put 0, which is the root rank or the remote leader of group A. So we have seen this one already, MPI intercom create. This is how how we had that original intercommunicator. But now what we want to do is that we want to create a new intercom group. So that is the new intercom group. So this is going to be all the processes in group A. Let's say we want to have a selection of those ranks. So far up until this point, what we did is that we put processes 0 through 5 in group A, and we put processes, the next 5 processes in group B. And now what we want to do is we want to take a subgroup of group A, which is processes 1 and 2. So that is why we put this color 0. So all processes in group A are going to come to here. And that's those 2 processes, process 1 and 2, are going to get selected. Again, we use those operations which we have seen for group management. So we basically try to get that intercommunicator passing this group A, which we have created earlier. And we want to have this group include group A, two processes. The process we are interested are process number 1 and process number 2, or rank number 1 and rank number 2. Those are the selected ranks. And then we pass in this new intercommunicator group, which we have basically allocated outside of this. So everybody has a copy, like all the processes has a copy of this new intercommunicator group, but this new intercommunicator group is going to be different for processes in group A and for processes in group B. Processes in group A are going to have this selected processes, and we're going to free that group A that we created earlier because we wanted to have so this call here, MPI com group, basically takes all the processes which are in this intercommunicator, and it tries with this include sort of constructor, tries to take only process 1 and 2 from all those processes in group A. And then we're going to have the same thing in group B. First, we're going to basically take all the processes in group B, and then we're going to select only 3 processes, 0, 3, and 4, 0, 3, and 4 from that group B. And then, we can, once we're done with that, we can free that group as well. And then the local rank, the root of group B and root of group A can basically print those information for us. And finally, we create this new intercommunicator. And then with a call into MPI com create, we pass in the intercommunicator as the first argument, which was a communicator. In this case, it's not an intra-communicator, it's an intercommunicator. Then we pass in this new intercommunicator group. That's the subset group that we were interested in. Notice that for processes in group A, it's going to be those selected processes of 1 and 2. And for processes in group B, it's going to be those selected processes 0, 3, and 4. And then you pass in this new intercommunicator. So this group A prime, which is basically this group A and the second, like this after, is going to be 0 and 1. So that is processes 1 and 2 in group A. And group B prime is going to be processes 0, 1, and 2, which is corresponding to 0, 3, and 4. So that is procs 0, 3, and 4 in group B. And then we say if the new communicator is not MPI com null, so only those valid processes are going to come here, print some information, and only those valid processes needs to free that communicator. And then we have some freeing to do for all the processes, that group that we generated, the local communicator, which we want to, we generated that for the original intercommunicator we wanted to create, and the intercommunicator, which is the original intercommunicator. So let's go back. This example is very beautiful. MPI CC MPI com, create inter. And if I run it, of course it doesn't work with 8 because we said we need 11 processes. And you can see that selected processes from group A are 1 and 2. Selected processes in group B are processes 0, 3, and 4. And you can see that these are the world rank of those processes. So process 1 and process 2 are basically from group A, so these two processes, and processes 0, 3, and 4 in the world group, they have these ranks basically, 6, 9, and 10. So that's it. It's a very beautiful example, which we tried to mimic from this illustration in MPI standard. Okay, now we can continue. So this is the example that we don't care. The next one on the line is MPI com create group. We have an example for that, MPI com create group. It takes a communicator, and notice that this cannot be an intercommunicator. It is explicitly an intra-communicator. That is super important to notice. It is not similar to MPI com create. So you cannot pass in an intercommunicator here. And then you pass in a group here which is a subset of the group of com, again here, a subset of this group. And then you pass in a tag that's an integer, and then you pass the new communicator here, which should be a pointer to that. So MPI com create group is similar to MPI com create. However, MPI com create must be called by all MPI processes in the group of communicator, whereas MPI com create group must be called by all MPI processes in group, which is a subset of that group of corresponding to the communicator. So that is the major distinction between the two. I'm not going to read the rest here. So continuing from here, it says if the calling MPI process is a member of the group given as the group argument, then new communicator is a communicator with group as its associated group. If the calling MPI process is not a member of group, for example, group MPI group empty, then the call is a local operation and MPI com null is going to get returned into a new communicator. That is also super important. The tag argument doesn't conflict with tags used in point-to-point communication and is not permitted to be a wildcard as well. This is super important. I'm going to highlight that as well. So if multiple threads at a given MPI process perform concurrent MPI com create group operations, then the user must distinguish these operations by providing different tag or com arguments. We have an advice to users. MPI com create may provide lower overhead than MPI com create group, because it can take advantage of collective communication on communicator when constructing new communicator. That is an advice. So this means that MPI com create has less overhead and probably computationally more efficient. So before going to MPI com split, let's take a look at the example for this one. MPI com create group, vim MPI com create, group. So these are the same. Again, notice that we're going to use at least 8 processes here. Same drill here. We have the world group, G size, G rank. They're going to be the same as rank and size. Then root process prints some information. We want to create the new communicator. That's the custom group, processes 2 and 3. We have the custom communicator, and then with group include, we create that custom group, which holds processes 2 and 3 in it. We have the new ranks with group translate ranks. We can see the corresponding ranks of processes 2 and 3 in the new custom group. And processes 2 and 3, you see that we have an isolation call here, so sort of an isolation if block here, so that only processes 2 and 3 must be called by all procs in the group. So in the previous example with MPI com create, we said all processes that are part of the group of the original communicator are going to call this a function. But in this case, all the processes only as the subset of that group, which is that subset is only processes 2 and 3. So that is that sort of if block, the isolation call. So they are the ones who need to basically call this MPI com create group. They pass in the MPI com world, they pass in the custom group, they put a tag here as 42, and then they pass in the custom communicator. And then again, we use the comparison. We want to compare MPI com world with the custom communicator that we created a second earlier. And of course, these are not going to be equal. So this is supposedly the output of this result. And then also notice that only processes 2 and 3 are responsible to free their custom communicator, because the rest of them are not going to have anything in them. So freeing, this is common for all processes because we have created the custom group and world group so that every process needs to basically free. So let's do MPI CC MPI com create group and run this. With 11 processes, of course, the size and group size is going to be exactly the same, and this is the rank of the root process. Out of those 11 processes, we selected process 2 and 3. Their custom rank in the custom group is 0 and 1, 0 corresponding to process 2, 1 corresponding to process 3, and process 2 in this case prints that MPI com world is not equal to the custom communicator that we created with MPI com create group. So there we go. The next thing on the line is MPI com split. You pass in, okay, we have seen this sort of in all the examples pretty much that we had in collective communications in the intercommunication scenario, we have used this MPI split. So I don't have a separate example for this one, but we have seen this this pattern, right? So you pass in your communicator, you pass in a color function or a control of subset assignment, a color function. It's not a function. I call it as a color function because it basically can create different subsets of the original communicator. And then you pass in a key. That key controls the rank assignment in the corresponding new communicators. And the new communicator is going to be the output. So this function partitions the group associated with communicator into disjoint subgroups. Notice that it's not a subgroup. It can be different subgroups. So you can have, depending on how many colors you associate your original processes in the original communicator, you're going to have different disjoint subgroups. You see that they're going to be disjoint. They have to be disjoint. Disjoint means non-overlapping. One for each value of color. So if you have like 3 colors, you're going to have 3 separate sub-communicators. Each subgroup contains all MPI processes of the same color. Within each subgroup, the MPI processes are ranked in the order defined by the value of the argument key, with ties broken according to their rank in the old group. A new communicator is created for each subgroup and returned into a new communicator. An MPI process may supply the color value of MPI undefined, which means that in which case a new communicator is going to return MPI null. So this is a collective call, super important, but each MPI process is permitted to provide different values for color and key. No cached information propagates from communicator to new communicator, and no virtual topology information is added to the created communicator, which is pretty much the same scenario with all the operations we have had so far. With an inter-communicator a call to MPI create, group new is equivalent to a call to MPI split with color key new where MPI processes that are members of their group arguments provide a color argument equal to the number of the group based on a unique numbering system for all disjoint groups, and a key argument equal to the rank in the group. And all MPI processes that are not members of their group argument provide a color argument which is equal to MPI undefined. In that case, they're going to get the MPI null. So the value of color must be non-negative or MPI undefined. That is super important. Okay, we have an advice to users that this is an extremely powerful mechanism for dividing a single communicating group of MPI processes into K subgroups. How do we do K subgroups? We do it implicitly with a number of colors that we select. So if you have K colors, we're going to have K subgroups of those MPI processes. Each resulting communicator will be non-overlapping. We said they're going to be disjoint. Such a division could be useful for defining a hierarchy of computations such as multi-grid or linear algebra. For inter-communicator, MPI split provides similar capability as MPI create to split a communicating group into disjoint subgroups. MPI split is useful when some MPI processes do not have complete information of the other MPI, other members in their group, but all MPI processes know the color of the group to which they belong. In this case, the MPI implementation discovers the other group members via the communication. So MPI create is useful when all MPI processes have complete information of the member of the groups. In this case, MPI can avoid the extra communication required to discover group membership, right? MPI create group, that's the last one, is useful when all MPI processes in a given group have complete information of the members of their group, and synchronization with MPI processes outside the group can be avoided. So this paragraph, I think it's a super important one. And I think it was quite clear as well. So we have a rationale here. Color is restricted to be non-negative so as not to conflict with the value assigned to MPI undefined. So this is a simple rationale. The result of MPI comes split on an intercommunicator. Okay, do we have an example for this one? Oh no, we don't. We said we don't have an example for this one because we have seen this pattern pretty much everywhere when we have this. Let's go with MPI come create inter, for example. In all those inter scenarios, we had always this splitting, right? And we were using basically this MPI come split. So this is the intercommunicator that we have. This is the color function that we have, which we basically use this division, which we say that if the rank of the process is less than or equal to, it can be less than, but this was for the case that we had when we wanted to have the equal sign here to include the last process into group A. Yeah, so we color them. So part of those processes are going to have the color of 0. The other part of those processes are going to have color 1. So in this case, we only use binary colors, 0 and 1. And we ended up with having two sort of sub-communicators, which are basically reflected into this local communicator. So local communicator can represent group A, and local communicator can also represent group B. If you are processing group A, local communicator is basically all the processes in that group. And if you are a processing group B, local communicator is going to be a communicator for all the processes in that group. Same way we had that local size. So we don't have a separate example for this MPI come split because we have seen it all over and over, but we do have an example for the case that we have MPI come split intercommunicator scenario. Again, here we beautifully, we try to mimic the same sort of visual representation here into an example called MPI come split up. I made a mistake, sorry. Come split inter. So again, we used only 9 processes, and the reason for that because we have 5 processes on the left, 4 processes on the right, so the summation of the two is going to be 9 processes. Note that the first index here shows the color and the second index shows the key. Do not basically get deceived by the complications in this visualization. Let's break it down. So the first value or the first number shows the processes. So process 0, process 1, process 2, process 3, process 4. That's in left group. And in the right group, this is process 0, process 1, process 2, and process 3. That's it. So this is the first number. We already know what that means. Then we have the color. So how many colors we have shows how many subgroups or subcommunicators we're going to have in the end. So let's see. The first one is the color. So we have color 0, color 0, color 1, color 2, and color 2. So we have 0, 1, and 2. So we have 3 colors. So this means if we have 3 colors on the left group, we must have 3 colors on the right group as well. So you see that color 0, color 1, color 0, color 2. Again, we have colors 0, 1, and 2. The resulting sub intercommunicators are going to be depending on sort of the color that we have. For example, on the left group, we have color 0, color 0. So this means these two processes, 24 minutes is over. I'm going to finish this sort of explanation, and then we're going to continue in the next episode. So notice that this is color 0, this is color 0. So process 0 and process 1, process 0, process 1, they belong into the first category of intercommunicators. Color 0, color 1, color 2, color 0. So processes 0 and 3, processes 0 and 3 are in the first category. Color number 1 is here, process number 4. There's no other processes with color 1. So that is why process number 4 is alone in the second category. This one has a color 1. No other processes has color 1. So that is why, again, we have an alone process here. Again, the next one is 2. Process number 2 has the color 2. Process number 3 has the color 2. So we should have process 2 and process 3. And on the right hand side, or on the right group, we have process 2 with the color of 2. That's the only process we have. So that is why we have the all process. Notice that they put inside the parentheses in the rank of the original group. So this is color 1. This is sort of the first intercommunicator we have. This is, sorry, color 0, the first intercommunicator we have. Color 1, the second intercommunicator we have. And color 2 is going to be the third intercommunicator we have. So notice that beautifully, with this MPI comes split. With this MPI comes split, in the case of intercommunicator, first or originally we had one intercommunicator, group A and group B. Now we have subdivided it into 3 intercommunicators, with group A having processes 0 and 1, having processes 0 and 3. Then we have another intercommunicator with processes 4, processes 1 in group A and B, or you can say group A prime and B prime. And in the third category of intercommunicator, we have processes 2 and 3 as A double prime and B double prime. So that is how it looks. So I'm going to show the example in the next episode.